Hello there, Mr. Sutton here with the BC Calculus 7-4 Extra Practice number 3 solutions on Taylor series. On this question, we're given this f function and we have a whole bunch of information about f and its derivatives at x equals 1. Based on this, they want the third order Taylor polynomial at x equals 1, and then we have to use that to approximate f of 1.2. So let's get the polynomial first. So I have f of 1 plus f prime of 1 times x minus 1. That's going to be the next format for the term. And then after that, we'll have f double prime x minus 1 squared over 2 factorial, and f triple prime 1 x minus 1 cubed over 3 factorial. Now plugging in some actual values, f of 1 they said was 4. F prime was negative 1, so this is negative x minus 1. F double prime is 3, so we have 3 times this stuff over 2 factorial, or I can actually just make that 2. And for this next one, I've got 2 times x minus 1 cubed over 3 factorial. That's really 2 over 6, which I can reduce to 1/3. No real need to reduce it, but I'm going to, just so I have less things to plug in my calculator. Now to approximate f of 1.2, that's going to be approximately equal to p sub 3 of 1.2, which means I'm basically going to plug 1.2 into all this in the calculator. So here I am on my calculator. I've plugged this p sub 3 polynomial in for my y1. I didn't necessarily have to, but I think it's going to be a little bit cleaner this way. So let me x out of there and do alpha trace y1 of 1.2. This way, I let the calculator deal with all the plugging in the parentheses. Enter. That comes out to 3.863 approximately. So there we are. For this problem, we want the coefficient of x to the fourth in the Maclaurin series, generated by cosine of 3x. Well, what's the series for just cosine of x? That's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And that's probably enough if we've got an x to the fourth, because we were looking for the coefficient of x to the fourth. So let's take it one step further and apply this transformation here of having 3x instead of x in there. So that's going to just plug a 3x in for all the x values. And you notice I didn't bother writing anything else because I know at this point that it's this x to the fourth term that I'm really the most interested in. So if I apply this fourth power here, this is going to be 81x to the fourth over 4 factorial. And 4 factorial, that's going to be, let's see here, 4 times 3 times 2 times 1. So that's going to be 24 down there. So I have 81 over 24 x to the fourth. So the coefficient is just going to be 81 over 24, but that's none of these answer choices. So I need to reduce that. These are both divisible by 3, so that ends up being 27 over 8. And that's our coefficient, 27 over 8, so choice A. For this calculator-based question, we have a function that has derivatives of all orders with all this information about the function f at x equals 2. We've got the value and the first 3 derivatives. We want to use a third degree Taylor polynomial for f about x equals 2 to find the approximation of f of 2.1. So there's no way to do this problem other than actually setting up this polynomial and plugging 2.1 into it. So for our general setup, we're going to have f of 2 plus f prime of 2 times, let's see here, since this is about 2, we're going to have x minus 2. After that, we're going to have f double prime of 2 times x minus 2 squared. And don't forget there's also a 2 factorial that we're dividing by. And for our third term, this will be f triple prime of 2 times x minus 2 cubed over 3 factorial. Don't forget those factorials. There's absolutely an answer choice for people who forget them. All right, so now let's actually apply some numbers. F of 2 was just negative 1. F prime of 2 was 4, so we have 4x parentheses x minus 2. F double prime of 2 is 6, so this is 6x minus 2 squared over 2 factorial. And for this last one, this is going to be 12, f triple prime of 2, 12 times x minus 2 cubed over 3 factorial. At this point, there's nothing else to do except plug in 2.1 and hope for the best. So that's what I will do. I can say f of 2.1 approximately equals this third degree, third order polynomial of 2.1, and the rest is up to my calculator. So to make my job all that much more easy and accurate, I've actually gone into my y equals in y1 and entered exactly as I see it here, that whole polynomial that I just wrote, that whole P3. So what I'm going to do now is quit out of there, and I'm just going to do alpha trace y1, and now I'm just going to plug 2.1 into that, open and close the parentheses next to it. So this saves me the trouble of having to write 2.1 minus 2, 2.1 minus 2 the whole way across. Just let my calculator do all that number crunching for me. So pressing enter, this comes out to, well, exactly negative 0.568. Didn't expect it to be so precise. So I can actually write equals after that. So that's going to be choice B. On this problem, we have some values of h and its first three derivatives in this table. We want to approximate h of 1.7 using a third degree Taylor polynomial for h about x equals 2. So the general setup for this polynomial, which I'm going to call p sub 3, is going to be h of 2 plus h prime of 2 times x minus 2. We're just using our Taylor formula here. And then we'll have h double prime of 2 times x minus 2 squared over 2 factorial. And then finally, h triple prime of 2 times x minus 2 cubed over 3 factorial. Plugging in some numbers here, h of 2 they set up here, that was 7.32. And then we have h prime of 2, that's 4.63 times x minus 2. H double prime of 2 was 9.68, so that's the only change to that piece. And instead of h triple prime of 2, I'm going to write in the value of 48.6. And at this point, all I have to do to approximate h of 1.7 is to plug 1.7 into p of 3, p3. So let me do that on the calculator. So just to make my life a little bit easier, I've actually gone into my y equals and I've entered p sub 3 exactly as I see it on the page there. So everything is completely identical. I've got x's and everything else. I think it's easier to enter this with x's first and then quit out of there and go to alpha trace y1 and just plug the number in this way instead of replacing all these x's in here with 1.7s on your own. Just let the calculator do all of that. Press enter, and that comes out to approximately 6.148. So that's choice C. On this one, we have values of a function f and its first three derivatives at x equals 5 given by this table. We want the third degree Taylor polynomial for f about x equals 5. So general setup for this, we're going to have f of 5 for that first term, whatever that is. After that, we'll have f prime of 5 times x minus 5 in a parentheses. And then f double prime of 5 times x minus 5 squared over 2 factorial. And then finally, continuing to use this Taylor formula here, we have f triple prime of 5, x minus 5 cubed over 3 factorial. Time to plug in some values from our table. F of 5 was just 2 in the table. So we've got 2, and then we're going to have minus 1, or just minus, parentheses, x minus 5. After that, for f double prime, we've got 8. So 8 x minus 5 squared over 2 factorial, which is going to be 4 if I reduce that. And the answer choices are all reduced, so we might as well reduce as we go. And then finally, f triple prime of 5, that's 18. 3 factorial is 6, so 18 over 6 gives us 3 x minus 5 quantity cubed. And that ends up being, let's see, they all start with 2. Choice A is the only one that doesn't have the x minus 5 after that. Then we have a 4 x minus 5 squared. That's in choices B and C. But on the last term, we differentiate these two, not in a calculus way, just making them look different. B is our answer. It's got the 3 there at the end.